So ultimately we're going to want to understand what are called infinite series, which is an important idea in calculus. But before we do that, we're going to need to lay some groundwork by studying what are called sequences. So informally speaking, a sequence is just a list of numbers written in an explicit order. And so here you'll see some notation. You see the swirly brackets here with the a sub n, and then that's just notation to represent the list of numbers, and the subscripts represent the placement of the numbers in the list. So a sub 1 means that's the first number in the list. A sub 2 means that's the second number in the list. And a sub n means that's the nth number in the list. This subscript notation is often used in calculus textbooks, even though you could use function notation such as f of n, and we'll see why that makes sense as well. But it's more common, I think, to see the subscripts. The other notation you might see is sometimes you can just see the sequence and its explicit definition written out. So a sub n equals, n over n plus 1. All right. So there's a few different ways of representing sequences. All of them convey the same underlying idea. So two that you really want to understand are arithmetic and geometric sequences. And so the structure of both of these are completely well defined, and we can actually sort of apply a procedure to find the explicit and recursive formula for any one of them. So for instance, an arithmetic sequence would be something along the lines of 2, 5, 8, 11, 14. And so what you'll notice is in that sense, I'm just adding, I'm starting with a number 2 and I'm adding the same number to get new numbers. So I'm just adding 3 every single time. So anytime you notice a sequence is written like this, then its structure is always on some number plus the common difference, that number plus the common difference twice, etc. And so the recursive formula for that would be written like this. You've got your first term determined or identified, so a sub 1 is 2. And then you'd be saying in general that any term, so a sub n means any term, is the one before it, represented by a sub n minus 1, plus the common difference. An explicit formula would be one in which we can actually plug in any integer, like 20, and the formula should give out the 20th term in the list. So for an arithmetic, it always follows this same structure. Your explicit formula is always your first term plus your difference added n minus 1 times. So I'm going to omit some of the details of how to come up with that, only because I'm going to get to more interesting stuff as it relates to calculus. So I'm assuming sort of your pre-calculus and Algebra 2 teachers did a sufficient job of helping you understand where these come from. But this is just a quick review. A geometric sequence would be one like 2, 6, 18, 54. So if you notice, in this case, you're starting with a number and you're multiplying by what's called the common ratio every time. And so symbolically, we start with a number, we multiply that number times the common ratio once to get the next term, twice to get the third term, 3 times to get the fourth term, and n minus 1 times to get the nth term. So its recursive rule would be start with your first term, define it, and then any term is the one before it times the common ratio. An explicit form would be any term is the first term times the common ratio multiplied n minus 1 times. Okay, so there's just an overview of what a sequence is and two very common sequences that tend to show up a lot. We mentioned informally that a sequence is just a list of number written in a specific order. Formally, a sequence can be thought of as a function whose domain is the set of positive integers, usually 1, 2, 3, 4, 5, etc. So again, thinking of a sequence as a function actually will turn out to be pretty useful later on. And you can again just think of it as a function where you're only inputting positive integers and the outputs are whatever the outputs may be. So in that sense, you can think of a graph being associated with a sequence. You've got the point 1, a sub 1, 2, a sub 2, 3, a sub 3, etc. And with a graph, it can help us understand certain things like what are the terms of the sequence heading towards as n gets really big. And I've listed out here some steps that you can apply on your calculator if you want to get a graph. So I won't go through that because to be honest, it's not the most essential thing in a calculus course. I don't know how often this ends up being used. But here's one way of doing it if you go into parametric mode. Let's just graph this sequence quickly so we can see what the picture would look like. So a sub n is defined to be n over n squared plus 1, and we're inputting n values starting at 1 and going off forever. So we'll just list out the first three terms. The first term will be 1 over 1 squared plus 1. That was a poor n squared. 1 over 1 squared plus 1, which would be 1/2. And the second term looks like it would be 2 over 2 squared plus 1, which is 2 over 5. I'm going to omit some of the details now. The third term would be 3 over 10. The fourth would be 4 over 17. And we'll do one more. The fifth would be 5 over 26. So let's graph these points. I'm going to graph 1, 1/2. I'm going to graph 2, 2/5, which is about 0.4, so it gives you a sense of where to locate it. I'm going to graph 3, 3/10. I'm going to graph 4, 4/17, which is just a little bit smaller than a fourth. Now at this point our graph, we're not really concerned so much about precision, but just the overall shape. And then 5/26, which is roughly a fifth. And so I think you can anticipate generally what the graph's going to do. It looks like it really should never get below 0, because there's nothing you can plug in that would make this a negative number, especially since we're squaring that n at the bottom. And we're only plugging in positive integers, so that's another reason. But it should end up just looking somewhat like this, and at this point we can't really get the details. But again, it's a graph. We do not connect these dots because it's a graph whose domain are the positive integers. And this picture gives you a good sense of what's happening as n goes to infinity. Right? Looks like the sequences are starting to approach 0, or tend to approach 0 as n gets large. I'll finish just by giving you yet another way of actually graphing sequences in your calculator. This is one way of graphing what are called recursive sequences, which are, again, sequences defined in terms of previous terms. So we'll graph this. I'll let you explore this on your calculator on your own. So I've got here a recursively defined sequence. I've got my first term. Any term is the one before it plus 4, and of course that rule applies as long as your n is bigger than or equal to 2. So let's get the first few terms. We'll graph them, and that will conclude our look at an introduction to sequences. So I've got my first term is 2. I've got that my second term is according to this rule. So since n is 2, n minus 1 would be 1. It's my first term plus 4, which is 2 plus 4, which is 6. My third term would be, well, my second term plus 4 which would be 6 plus 4, which would be 10. We'll do one more. My fourth term would be my third term plus 4, which is 10 plus 4, which is 14. So you can see, if you just look at the pattern, that our first number is a 2, then it's a 6, a 10, and a 4. Every time we're just each term is just 4 more than the one before it. So if we graph these, we should make a scale, I guess. 1, 2, 3, 4. So we're going to graph 1, 2, since the first term is 2. We're going to graph 2, 6. We're going to graph 3, 10. And we're going to graph 4, 14. I think my scale's a little off, but maybe we can just stop there. So you can see that these terms are situated on a line, and it's clear from the graph that as n goes to infinity, then the terms are going off to infinity as well.